All right, today we are diving into what I like to call the fundamental grammar of mathematical spaces. We're going to crack open two key theorems that basically dictate how these spaces can combine. And trust me, this is going to feel a lot more like a detective story than some dry math lecture. So, to get started, just imagine something for me. Think of a vector space not as, a bunch of boring numbers, but as its own self-contained universe. It has its own dimensions, its own objects, we call them vectors, and its own super strict set of physical laws. So that brings up a really cool question. What happens when two of these universes actually collide? Now, the specific universes we're talking about today are called vector subspaces. The best way to think of them is like a tiny universe living inside a much larger one. But here's the catch. For it to even exist, it has to obey three totally non-negotiable laws. If it breaks even one, well, its entire reality just collapses. And here they are, those three critical laws. First, every subspace has to have a center, an origin point, and that's the zero vector. It just can't be a completely empty void. Second, it's got to be closed under addition. What does that mean? It just means if you take any two things from inside this universe and add them together, the result can't just get teleported somewhere else. Nope, it has to stay inside. And third, it's closed under scalar multiplication. That's a fancy way of saying you can stretch, shrink, or reverse any vector, and the result still belongs to that same universe. These are our rules of the game. Okay, let's get to our first case file, the intersection. This is all about the region where two of our universes overlap. So the big mystery we need to solve is whether this new shared space is a legitimate universe in its own right. I mean, does it follow the three laws? Well, the official claim, our first theorem, is that the answer is always yes. The intersection of any two subspaces is always a subspace itself. Now, that's a pretty bold claim, right? Let's see if the evidence actually holds up. All right, time to play detective. We're going to take this new intersection space and we're going to check it against our three fundamental laws. If it passes all three tests, the theorem holds, and we've officially discovered a brand new, valid subspace. Okay, law number one, does it have a zero vector? Well, think about it. Since both of the original subspaces, let's call them U and W, had to have the zero vector just to exist, their shared area must also contain it. So check. Now, for law number two, closure under addition. If we grab two vectors from that intersection, that means they exist in U and they exist in W. And since U and W are already valid subspaces, adding those vectors together gives a result that's also in U and also in W. So if it's in both, it has to be in their overlap. Check. Again, so far, so good. And finally, law number three. It follows the exact same logic. You take a vector from the intersection, you scale it up or down, and it's guaranteed to stay within U and stay within W. Therefore, it has to stay within the intersection. So, with all three laws satisfied, our investigation is complete. The intersection is a stable, totally predictable way to form a new subspace. Case closed. But now, let's move on to our second mystery, which, seems like it should be just as simple: the union. This time, instead of just looking at their overlap, what if we try to merge two universes completely, taking everything from both of them and just mushing it all together? I mean, this feels like it should have a really obvious answer, doesn't it? We just proved that the intersection works perfectly every single time. So merging them, taking all the parts of both, that should definitely create a bigger, perfectly valid subspace, shouldn't it? And here's the twist. The answer is no, not always. Merging two subspaces just doesn't always work. And this is where our investigation gets really interesting, because it completely breaks our expectations. The full story actually comes from our second theorem, which gives us this very specific and honestly pretty surprising condition. The union of two subspaces creates a valid new subspace if and only if one of the original subspaces was already completely inside the other one to begin with. And this is a great way to picture the rule. Look, if one universe is just a smaller version that's already living entirely inside another one, their union is just the bigger universe, which we already know is valid. But look at the other side, the unstable condition. If they only partially overlap, you could take one vector that's only in the first universe and add it to a vector that's only in the second. Their sum could easily land in a location that isn't in either of the originals. And boom, you've broken the law of closure. The combined reality is just unstable. One of our sources, Dr. Gajendra Purohit, puts it perfectly. He says, the union is a subspace only when they contain in each other. That condition is the absolute key. It's not about just merging things. It's about whether one space already encompasses the other. So how do mathematicians actually prove this? Well, they use this really clever trick called proof by contradiction. They start by assuming the opposite is true, that the union is a subspace even when neither contains the other. And then they show step by step how that assumption inevitably leads to breaking one of those fundamental laws we talked about, proving it's completely impossible. So we've solved our two mysteries. We have our answers. But why does any of this actually matter outside of a math class? What's the big reveal here? Let's break down the key takeaways from our little investigation. First, the intersection is robust, it's reliable, it always works. It's how you safely find the common ground between different mathematical spaces. The union, on the other hand, is fragile. It only works under this very special condition, which makes it a much, much more delicate operation. And believe me, this isn't just some abstract exercise. This grammar, these rules for combining spaces, it's foundational to so many fields. In computer graphics, it literally defines how objects can intersect on your screen. In data science, it helps us analyze overlapping data sets. And in quantum computing, it describes how different quantum states can be combined. These rules are building the digital and physical worlds all around us. So we've learned the strict laws for combining these mathematical universes. But that leaves us with one final, pretty fascinating question to think about. If these are the rules for putting subspaces together, then what are the rules for taking them apart? Well, that's a story for another time. Thanks for joining.